Yes, I'm going to talk about the benefits and challenges of very low Earth orbit today. This is an update, a little bit of the masterclass that Peter gave before at one of the Discoverer General Assembly meetings, which is available on YouTube. So if you want to go and have a look at that as a recap, then you can. But also a summary of our work that we published also in Progress in Aerospace Sciences as part of the project. There is also a link that will be available at that paper as well that goes into a little bit more detail. So I'm going to start with what is a very low Earth orbit. In Peter's video, we discussed a little bit the definition, and we've standardized that around 450 kilometers in altitude. And basically that's where we see that the aerodynamic effects become significant and we can't ignore them in the design of our satellites. And these very low Earth orbits, they're not entirely unexploited. Earlier, back at the start of the kind of exploitation of space, they were used for reconnaissance. And that's principally, as I'll discuss very shortly, because of the proximity to the Earth's surface. The International Space Station orbits around 400 kilometers. That's definitely within our VLEO range. And there's been a range of other experimental or scientific missions that have orbited lower as well. So, for example, we have here Goche, which orbited below 300 kilometers for part of the mission. And then more recently, there's been a range of different commercial CubeSats or nanosatellites. Academic institutions have used them as well. So commercially, it's principally two companies called Planet and Spire. However, they've also, more recently than that, started to deploy their satellites higher. And I'll come on to that later about some of the challenges that are associated with operating in very low Earth orbit. But principally, we have three kind of areas to look at here. So why are we interested in operating in VLEO in the first place? And that's because there are a range of benefits that can be afforded by operating in this orbital range. Why hasn't VLEO been a commercial success yet? And these are associated, or this is associated with the challenges that we have of operating in VLEO. And what can we do about it? So how can we actually move into exploiting VLEO? What are the opportunities that we have with current technology to mean that we can actually start to operate there? The first thing to note here is that the environment in very low Earth orbits is substantially different to that in higher low Earth orbits. Principally, it is due to the increasing atmospheric density that we get as we reduce in altitude. So you'll see here in the figure on the right-hand side of the screen that I've plotted the variation in atmospheric density with altitude. And as we stray below that line of 450 kilometers, you'll see that the order of magnitude of the density increases substantially. It remains in a free molecular flow regime, so that's rarefied flow, but the density increases significantly. The background of the figure, you'll also see atomic oxygen in that orbital regime is relatively high. At the lower end, it starts to get traded out for nitrogen, but as the density increases, that atomic oxygen remains in high abundance. It's also, because of the orbital velocity, highly energetic, and we'll talk about that a little bit later in the challenges that are associated with this atomic oxygen. And finally, this whole regime is associated with quite a lot of uncertainty and a lack of knowledge with a lot of the mechanisms that are present there. So we know that the density, for example, and you'll see from the different lines that I've plotted on the figure, varies with the solar cycle. So there's quite a lot of variation in there. Also, our knowledge of the exact values here is quite poor. We have models for it, but they're there's a lot of uncertainty associated with that. And there are also the presence of thermospheric winds, which we find very difficult to predict. We have models for those as well, but again, full of uncertainty. So as we go through some of the benefits and later the challenges, we have to bear in mind that this environment in very low Earth orbit is challenging and also full of uncertainty. Moving on to some of the benefits that we have of operating in very low Earth orbit. I'm going to start here with optical resolution, and we have an equation there which equates the ground resolution distance, so this is an expression of optical resolution, with the range to our target and the aperture diameter. And here on the right-hand side, I've plotted the diffraction limited resolution against the altitude. And as we see, as we come down in altitude, naturally, our resolution increases. For example, if we go from 600 kilometers to 300 kilometers, our spatial resolution is cut in half. You might also hear that as a doubling in resolution. It can be a little bit confusing about how people talk about it, but basically it's an improvement by a factor of 2. Associated with that, looking back at the equation, we could also decrease the size of our aperture by the same factor, and that might result in a significant reduction in the payload mass. And also, as we'll move on talking about the challenges later, if we're thinking specifically about aerodynamic drag, Having a smaller payload or a smaller aperture might also help us in the design of our spacecraft, because we can have smaller cross-sectional areas, reducing the drag. This is a very, very important benefit for Earth observing platforms, because we can get either higher resolution or we can have smaller payloads as we reduce the altitude of our operations. Provide an example here. This is just to kind of illustrate the increase in optical resolution that we might get from an example case of moving from 600 kilometers to 300 kilometers. So this is a picture of a stadium in Qatar. And you can notice the different features that you might be able to pick out at the different resolutions. So for example, in the top half of the image, you might find it very difficult to pick out how many cars are on a road, for example, or possibly if there are even kind of people or vehicles around. In the bottom half of the picture, that would be a lot clearer. You'd definitely be able to pick out vehicles, potentially even individuals or groups of people. The applications that you can do with this increased resolution are quite interesting. Another benefit associated with optical payloads is our radiometric performance. So for optical imaging, we essentially rely on kind of optical radiation to be reflected from a surface and received at our telescope on the satellite. And that power reduces with distance by 1/r². So if we are closer to our target, then we will receive more of that intensity, more of that power. Our collector power also increases with the square of the diameter, because it's associated with the area. So we get this relationship of d²/r². So basically we can say that our signal power improves with reducing altitude or increasing our aperture diameter. If we keep a fixed aperture, again, moving from 600 kilometers to 300 kilometers as an example, we get an improvement in received power of 4 times, or we can reduce our instrument sensitivity at these lower altitudes and get the same performance. And again, by reducing this complexity, we might result in smaller payloads, a reduced mass, and potentially cost reductions as well. Alternatively, if we keep our sensitivity the same, we can reduce our aperture diameter substantially whilst maintaining that performance level. So that's interesting as well. And this reduction in free space loss also applies to our communications link budget. So that's not necessarily optical, it's different parts of the spectrum, but we can get improvements in our link budget there as well, which will help us to downlink and uplink more data. Moving away from optical payloads and onto radar payloads. For a radar, it's an active sensing payload. So we project a signal from the satellite, we transmit a signal, it's reflected from a surface, and then it's received back at the satellite. So when you combine both legs of that transmission, we actually see a relationship with r⁴. So again, if we half our distance here, we actually reduce the power requirement to a 16th of that was required at the higher altitude. This is for a simple radar configuration. When we move on to a synthetic aperture radar, the relationship is a lot more complex. You'll see here from the equation that I've presented on the screen, we have the signal to noise ratio being related to the power, the area, and the range. There are a host of other factors in there, but we can essentially keep them constant, and they're associated more with the environment and the design of the payload. If we keep everything else equal, and again, we half our range, we can reduce by 1/8 or to 1/8 the transmitted power. We have a slightly more complex area with the antenna area, but we see that it reduces by a factor of 1/2.83, or we get an increase in our signal to noise ratio of 8 times. Okay, and you'll see from the figures here that I've plotted out that the relationship of the required transmitter power can also be related to both the altitude and the antenna range. So we can find a sweet spot as such in there that fits our design, the altitude that we're operating at, and the power that's available on the platform. We can similarly do the same with the sensitivity of the equipment, so the signal to noise ratio being traded against the antenna area and the altitude. Moving away from Earth observation and to communications, very briefly. This falls a little bit outside of the scope of Discoverer, but it's interesting to note anyway. We see that the latency, or the delay that we have in a signal, is also related directly to the range. So if we reduce our distance to our target by 1/2, then we see that the amount of time for that signal to propagate through free space is also cut in half. This is balanced a little bit if we have communications that need to pass over long distances, if there's handoff times between multiple satellites, processing on the satellite and on the ground. There are some additional kind of delays within there. The fundamental kind of time lost in the signal propagating is cut by a factor of 2. For communications as well, if you've had to deal with the ITU, you'll note that the bandwidth is being regulated and is limited significantly. As you get closer to the Earth with a spot beam or a cell of a given size, of a given kind of angular aperture opening, the size on the ground will decrease. Okay, so for a fixed beam width, the spot beam size reduces with reducing altitude. You can therefore use the same frequencies more frequently for a given area on the ground. So that's more channels per area, and also the capacity remains the same, so that you can actually serve more customers on the ground with a higher bandwidth, a lower altitude for the same amount of power. So from that perspective, by reducing the latency and increasing the amount of data that you can actually transfer over the network, there are some very interesting benefits for communications missions as well. Moving away a little bit from the kind of payload and mission performance and more onto the platform performance, we see that the radiation environment in very low Earth orbit actually improves a little bit as we go down in altitude as well. In low Earth orbit and very low Earth orbit, the radiation environment is largely from trapped electrons and protons trapped by the magnetic field, and they're very energetic. And we'll see from the plots here, so along the top, you have first on the left 300 kilometers and then 600 kilometers. And you can see that there's a reduced distribution of those electrons. The order of magnitude there is the same, but the distribution is reduced. And for protons at the bottom, you'll actually see that the order of magnitude drops. The number or the flux of the protons is significantly reduced, those energetic protons. And the benefits of that are reduced radiation dosing. So this means that we might be able to use more COTS components or consumer grade components on our spacecraft, and fewer components that need to be radiation hardened. That might translate into a significant reduction in both development and manufacturing costs of our spacecraft. We also might see an increase in the reliability of our radiation hardened or even COTS components over the mission lifetime as well. There might also be benefits to materials that have to persist in this environment for a long period of time. So particularly we see that the polymers might be affected by radiation dosing, and we might see benefits to that in very low Earth orbits. If we look at launch vehicles, and the plot here, I've shown the increase in payload mass capability to different altitudes of the same vehicles. And as we reduce in altitude, you'll see that for each vehicle, to differing effects or to differing degrees, we can launch a larger mass to a lower altitude. So in effect, the total capacity of each vehicle will increase to a lower altitude, or the cost per unit mass will decrease. So if you're able to launch as a cluster or as a rideshare, the cost of launch will decrease. And also, if there are more vehicles, you can launch your complete satellite, your group of satellites to a given altitude, then there's a little bit more availability, diversity, opportunity there. So you actually might even create a more competitive marketplace there. Looking again at our example from 600 to 300 kilometers, we see approximately a 10 to 50% improvement in capability depending on which launch vehicle we're looking at. So when it comes to end of missions, typically in LEO, satellites are, well, at the moment, a lot of them are left for debris, but there are now requirements for all satellites to be compliant with these IADC guidelines, which suggests that after the end of mission operations, a satellite is deorbited or moved to a graveyard within 25 years. In very low Earth orbit, we see that the time for natural deorbiting is reduced significantly. That's primarily because of the atmospheric drag that's present at these altitudes. Here in the figure, I've plotted for different solar flux units, so that's associated with the solar cycle, the time of the solar cycle, so low, medium, and high. And then for also different ballistic coefficients, so that's a geometric configuration of our satellite associating the area with the mass. And in general, for a reduction, again, a halving in the altitude, the time to deorbit is going to reduce by 2 orders of magnitude, so 1/100th of the time. This means that basically for all VLEO orbit, and for almost any kind of satellite design that you can consider with conventional materials, the guidelines of the IADC will be satisfied without having to incorporate additional deorbit hardware. So for example, drag sails. That could benefit the design, so we're not having to add additional components or systems, and it means that we don't have to worry about the kind of persistence of debris in the environment there. Moving on to the idea of debris, it's been well publicized now that debris in low Earth orbit poses a potential risk to operating there sustainably. In very low Earth orbit, the decay due to drag of all of the components or old satellites means that these vehicles or components, debris items, will fall through the altitudes and essentially burn up on re-entry. At higher low Earth orbit altitudes, this occurs very, very slowly, so over tens, maybe hundreds of years, at the top end of LEO, maybe even thousands of years. This means that very low Earth orbit altitudes remain resilient to buildup in orbital debris. The figures I plotted here discuss spatial density, so that's the number of objects in a given volume of space, and that illustrates the amount of debris in the environment there. If we want to actually consider real collision probabilities, then we have to do a much more complex analysis. And if we want to assess the risks, then we also have to consider the outcome of a collision. But spatial density gives us an idea of what the environment's like. And for both of these cases, we're looking at the change in the debris environment over the span of another 25 years, 30 years here. So we're looking all the way up till past 2050. And what you can see in the top figure up here is that our range of VLEO remains pretty resilient to any buildup in orbital debris. And as on the bottom of the figure, we've got an averaged case of that. And we see that, again, the spatial density remains very, very low in VLEO. So that means that our orbit range here remains very resilient to that buildup, and we retain a relatively low risk as a result of that. The geospatial accuracy is important, particularly for Earth observing payloads, so that we can actually locate a picture onto the surface of the globe. So our mapping errors due to azimuth and elevation, so these are associated with the attitude determination, we can see decrease as we reduce in altitude. And that's these two lines here on this figure. What that means is that our requirements on attitude determination of our spacecraft reduce as we reduce in altitude. There is a kind of slight converse effect here as well. So we also have pointing errors that are associated with our position knowledge. And we'll see that these increase, in fact, with reducing altitude. So you'll see that it's the cross track and the radial here increase with reducing altitude. What that means is that there's a modest increase in orbital position knowledge requirement with reducing altitude as well. We can do quite a lot about attitude determination and control in terms of the types of sensors that we include on our platform. And in fact, as we get into the kind of high requirements there, you get instruments like star trackers, which are quite expensive and difficult to implement on smaller platforms. In terms of orbital position knowledge, we're a little bit less kind of capable of affecting that. So we might use the same sensors, so star trackers can help in that orbital position knowledge, but our GPS is there and our ground-based sensors there to help us to position our satellites, kind of determine the position of our satellites. I'm going to move a little onto the challenges that are associated with very low Earth orbit now. You recall before that I discussing the variation in density that we see moving into the VLEO regime. And I'm now going to discuss the drag force, which I've given the equation for here, the very basic equation. So we've got the density and we've got the velocity, we've got an area of the satellite and the drag coefficient. And we can see that the drag force increases with density, also with the velocity, and both of these increase with a reduction in the altitude. You can see how drag force changes here by a number of orders of magnitude as we reduce in orbital altitude. To maintain a given orbital altitude, we would have to compensate for that drag force, and we would do that using a propulsion system. Over time, though, we may be able to partially compensate the drag and still achieve a useful lifetime in orbit as the spacecraft decays slowly. So there's two different kind of methods of operation here. So we either consider full drag compensation, where we can operate as long as our propulsion system has propellant or as long as our system can operate for, or we have a partial drag compensation, so we get a useful lifetime and slowly decay over time. But this is a significant challenge. It essentially puts a lifetime on a mission in VLEO that is of consequence. The aerodynamic torques that we see in the VLEO environment are also quite important to consider. On the graph here, I plotted the different environmental torques that would be associated with a given spacecraft platform. In this case, I've chosen the geometry of SOAR, which is our CubeSat that we'll be launching with Discoverer. And I've given it a certain configuration of the steerable fins and a certain attitude with respect to the oncoming flow. And as you can see, the aerodynamic torques become very significant over the reduction in altitude and bigger than even our residual magnetic dipole at about 300 kilometers altitude. So the aerodynamics definitely in this case can't be ignored, and that's to an extent part of our definition of VLEO itself. We also have to take into account when we're just thinking about these disturbing torques about the atmospheric co-rotation, so the orientation of our orbit with respect to that co-rotation, the thermospheric winds that we might not have that much kind of knowledge or associated with a lot of uncertainty, and also variations in density, because we know that the density will vary with the solar cycle and on shorter timescales as well, so day and night, and also seasonal variations. And as these aerodynamic perturbations become dominant, we might see reduced platform stability. We'll see increases in disturbing torques when we start to point out of the kind of nominal flow direction. And to kind of compensate for disturbing torques, we might have to increase the input from our attitude control actuators. And that might be associated with limit based on saturation or power consumption as well. So taking the aerodynamic attitude into account is important for the overall design and stability of our platform. I also mentioned before that the concentration or the composition of the atmosphere at VLEO is predominantly atomic oxygen. That atomic oxygen is highly reactive, and in association with the increasing density with reducing altitude, we see increases in the number of particle surface interactions of atomic oxygen. At orbital velocity, we have a high collision energy, and these atomic oxygen interactions can therefore be very damaging and erode our surfaces, particularly those that are forward facing into the flow. There will be effects on other surfaces as well, but it's predominantly the forward facing surfaces that we'll see the damage on. You can see some examples of these effects in the pictures. So the top one is both atomic oxygen and effects of ultraviolet radiation as well. And the bottom picture is an example of atomic oxygen erosion. That's the effect that's had on the general sample of the surface. And you'll see at the top, it's been protected, this small peak, by another particle here. In general, the atomic oxygen will also affect the aerodynamic properties of our satellite. So the atomic oxygen can adsorb to surfaces and change their properties, but also the interaction and erosion can cause chemical and physical changes to the surface that we have to be kind of taken into account as well. So those gas surface interactions are important for our aerodynamic performance. And we know that these gas surface interactions vary with the incidence of the surface with respect to the flow, the composition of the flow and its relative velocity, the surface composition, structure and roughness, its cleanliness and contamination, so for example by atomic oxygen, and also the temperature of both the surface and the incoming particles. There are two general kind of interaction mechanisms that we consider and combinations thereof. And I've given the figures of them here. So we have diffuse free emission. So our particles are basically impacted upon the surface and are emitted in any given direction. Or we see a specular reflection quality, basically like light in a perfect reflecting mirror. For our current materials, so materials that we have that are well characterized and are generally used on spacecraft, we see that the surfaces are highly contaminated in very low Earth orbit by atomic oxygen, and also that they generally erode as well. And this results in predominantly this diffuse free emission characteristic that we see. And this is important, looking at the figure on the right-hand side here, because of its effect on the drag coefficient and the lift coefficient here. So if we have diffuse re-emission and full accommodation, so that means the energy is absorbed by the surface of the satellite and the particle is essentially kind of re-emitted thermally from that surface, our drag coefficient is relatively high, even at shallow angles of incidence to the flow. We also see that the lift coefficient is orders of magnitude smaller than that, smaller than drag coefficient, so we don't get any useful lift forces either. If we could move to more specular reflection characteristics at very low or relatively low incidence angles to the flow, we can see that the drag coefficient is substantially reduced. So possibly to a tenth of the, or even lower than that of the diffuse case. And we can also see the lift coefficient that we can get from these materials is increased significantly as well. So potentially with opportunities for control, which I'll talk about in a minute. So if we're looking at the opportunity for developing or searching for novel materials for the space at the very low Earth orbit environment, we would look for those that are resistant to absorption and erosion of atomic oxygen and that would promote specular or quasi-specular reflection properties, with the benefits of reducing drag at shallow surface incidences and promoting lift force production. We'll note if I put that condition that it's shallow surface incidences, then we also have to consider the geometric design of our satellite so that it can mitigate that production of drag. We might see improvements in the aerodynamic control performance, and we could also use these materials for improving the performance of atmospheric intakes, another use there as well. Less important for very low Earth orbit or for the spacecraft that we're looking at, but these materials might also have applications for enhancing deorbit devices. So for example, drag sails, because you'll see that when the surface is almost normal to the flow, that the drag coefficient is actually increased significantly. So it produces more drag. There's also opportunities for using the drag and the lift forces for performing aerodynamic control in low Earth orbit. And that increases as well as a result of the increasing density, which means that the forces and torques are actually of larger magnitude and can be used effectively. Our potential applications for aerodynamic-based attitude control might be course pointing control, aerodynamic trim, so to reject those disturbing torques that I discussed before, or to help us to manage the momentum of our satellite or the momentum within the actuators, attitude actuators that we have. There are also applications in orbit control, so constellation deployment and management, or targeted re-entry. And I'm pretty sure later on in the sessions, we're going to hear some actual work that's been done within the scope of Discover on attitude and orbit control. So overall here, the opportunity lies in the development of new concept geometries for satellites, and the development of control methods using aerodynamics and their implementations. There's also a kind of less understood challenge in VLEO of potential spacecraft charging. So there's a number of different causes of charging of spacecraft in the general space environment, but also in the kind of lower and very low Earth orbit environments. We have a high flux of electrons in comparison to our ions, so that causes a generally negative charging effect. We have the fact that electrons generally penetrate wake regions more readily, so we get differential charging across spacecraft bodies. We get variation over an orbital period because of the variation in photoemission of electrons based on sunlight. If we have electric propulsion systems, then we require effective neutralization, otherwise we'll get attraction of those electrons. The bias on solar arrays, that tends to be positive, will also draw electrons away from these neutralizers for propulsion systems. So there's design effects that we have to consider there. And also if we have higher inclination orbits, then we have to consider the traverse of the aurora regions that can cause very rapid changes in charging on the spacecraft as well. Overall, the effects of this charging can be very damaging to the satellite. So we have consideration for onboard electronics, we have potential interference with measurements or sensors, and we potentially have parasitic loss on solar arrays as well, which would affect the overall efficiency of our power collection. So far, there's two kind of sides to this. So we can design our satellite to alleviate some of these problems. So we can encapsulate solar arrays or the conducting element of the solar arrays to avoid some of this leakage. And we can locate our thrusters and solar arrays relatively far from each other to prevent some of these effects. But looking further away from that, we can also develop new environmental models, new satellite models, and methods of prediction of this spacecraft charging so that we can design out some of these problems and operate better. A further challenge associated with moving closer to the Earth is that our coverage and access area reduce. So that's basically the footprint area of a given sensor becomes smaller the closer you get to the target. So this works essentially opposite to the fact that our spatial resolution is increasing or is benefited. If you look at high elevation angles, then we also get effects with the distance through the atmospheric medium as well. So that might affect our imaging quality. This also results in reducing communication windows, so our access times become shorter, and there's an impact on total data uplink and data downlink. So in general, this means that we can image a smaller area, or we can access a smaller area of the Earth's surface from a single satellite. Associated with that is the revisit time to any given point on the Earth as well. And you'll see from this plot that at the lower altitude range, there are fewer windows that have low maximum revisit time. And that might mean that we have to consider larger constellations of satellites to both give us the full coverage that we want and also the low revisit time so that we can come back and look at the same target multiple times in a given window. This access, coverage, and revisit has to be traded off against the other benefits that we have. We can address it somewhat through constellation design, but basically points us in the direction that not only do we need to think about the systems modeling of our satellite platform, but also the wider system itself. So if we're looking at constellation and ground segment design as well at the same time. Another opportunity that we have because of the higher density of the atmosphere at lower altitudes is that we can potentially use this residual atmosphere as propellant. This is a large part of the Discover project is looking at atmosphere breathing electric propulsion systems. Because we're not carrying the propellant at launch, basically the lifetime of our system is therefore not limited by the volume of propellant that's carried. And the lifetime of that system would be limited essentially by the degradation of the components, as long as it's operating in that environment with the right characteristics. And as I mentioned before, novel materials may also contribute to improvements in the collection efficiency. The opportunities that we have at the moment with these types of systems, these ABEP systems, is to develop the different individual system components, the intake and thrusters, and we know that that work is ongoing, but also there's opportunities in the systems modeling to resolve the design trades that are associated with ABEP. So the geometry of the thrusters, the amount of drag that's produced, the thrust that can be produced from the collected propellant, the amount of power that these systems need to operate, and also the solar array areas. And when you put all of these factors together, you get some interesting design loops and trades that have to be solved to actually generate a feasible solution. So I've got a relatively complex summary slide here, but I'll run through it very quickly. So we can look at all of these benefits, and I took that example of 600 kilometers to 300 kilometers as a reduction in altitude by a factor of 2. And we can see that in each of these cases, we can actually look at improvements. We get a twofold increase in the resolution, or a twofold improvement in the resolution, I should say, or a reduction in aperture diameter. We can get increased received power for radiometric payloads, or a reduction in the free space loss, so an improvement in free space loss. We get at least an 8-fold reduction in power for radars, so 8-fold for SAR, but 16 for traditional radar. We can halve latency for communications. We see an order of magnitude reduction of peak proton flux and a reduced range for the electrons over the surface over the globe as well. Launch vehicle performance is improved by approximately 10 to 50%, depending on the vehicle. And we see at least a 50-time reduction in the decay time for our end-of-life disposal, moving from 600 to 300 kilometers. That depends on the solar weather conditions and our ballistic coefficient. We see approximately 10-fold reduction in the spatial density of debris, contributes to our resilience against debris collision. And we also have a 2-fold reduction in our mapping error that's associated with attitude determination and control system requirements. We do have to acknowledge the challenges that there are in very low Earth orbit as well. So we know that there are the issues with atmospheric drag, which typically mandate some form of drag mitigation or drag compensation. We have the effects of atomic oxygen and the erosion. We have perturbations due to the aerodynamics at these altitudes. reduced coverage and access time, longer revisit times, and the effects of charging. We also have the opportunities and potential solutions to overcome many of these challenges. Implementing aerodynamic attitude and orbit control to help us effectively operate in and amongst those aerodynamic perturbations. Novel materials that will help to alleviate those effects of atomic oxygen, improve our aerodynamic performance, and also improve any atmospheric intakes that we might be interested in using. Development of atmosphere breathing electric propulsion systems that would help us to fully compensate for atmospheric drag, or in the very least mitigate that atmospheric drag to the point at which we can operate for a useful lifetime. And then also the development of kind of a holistic systems modeling and engineering environment so that we can consider all of the different benefits and all of the challenges and come out with some feasible and potentially commercially viable system designs as well.